Hello friends, welcome you all to the 49th lecture on function analysis and its applications. In this lecture we will discuss the further theorems on normal operators. This is the content of today's lecture. Further theorems of normal operators. Theorem: any arbitrary operator T and its adjoint T star on a Hilbert space H can be expressed as T is equal to T1 plus I T2 and T star is equal to T1 minus I T2, where T1 and T2 are self-adjoint operators on H. Proof: suppose T is any arbitrary operator T1 plus I T2, okay, and its operator T star is equal to T1 minus I T2, okay. Since T is equal to T1 plus I T2, so T star is equal to T1 plus I T2 star, okay. So this one is T1 star plus I bar T2 star, that is T1 minus I T2, where T1 and T2 are self-adjoint operators, okay. If you define T star is equal to T1 minus I T2, so we have to prove T1 and T2 are self-adjoint operators, okay. So let us prove it. Since T is equal to T1 plus I T2 and T star is equal to T1 minus I T2, adding these two, so we have T1 is equal to T plus T star by 2, and subtracting this from this, we have T2 is equal to 1 upon 2I into T minus T star. So let us prove T1 and T2 are self-adjoint. So here T1 is equal to this one, taking the adjoint of this operator as T1 star is equal to star of half T plus T star. So this can be written as 1 upon 2 into star of T plus T star, okay. We know that A plus B star is equal to A star plus B star by the property of adjoint operator. So this can be written as half T star plus star of T star, that is T double star, okay. And also we know that T double star equal to T. So T1 star is equal to half T star plus T, because T double star is equal to T. So this one is T1, okay. So this proves that T1 is self-adjoint. Similarly, T2 star is 1 upon 2I into T minus T star. So taking T2 star as 1 upon 2I bar, because we know that if alpha be any scalar and A be the operator, then star of alpha A is equal to alpha bar A star, okay. So 1 upon 2I as alpha, that is scalar, so 1 upon 2I bar here, and this one is star of T minus T star. Again, applying this property, so we have 1 upon I bar, that is minus I 1 upon 2I bar equal to 1 upon minus 2I. Okay. So this can be written as minus 1 upon 2I. And this is T star minus T double star. Again, applying T double star is equal to T. So we have minus 1 upon 2I T star minus T. Therefore, 1 upon 2I into T minus T star. This is T2. Okay. So here, this proves that T2 also a self-adjoint operator. Thus, any arbitrary operator T can be expressed in the form equation 1. This is the equation 1, where T1 and T2 are self-adjoint operators. Next, we shall show that the expression 1 for T is unique. If the expression is not unique, let T is equal to U1 plus I U2, where U1 and U2 are both self-adjoint operators on H. We have T star, that is star of U1 plus I U2. Applying this property, star of A plus B is equal to A star plus B star. So we have U1 star plus star of I U2. So I as scalar, that is, this is U1 star plus I bar U2 star. Okay. I bar is minus I. So this one as U1 star minus I U2 star, where U1 U2 both self-adjoint, that is U1 minus I U2. This is equation 2. But T is equal to U1 plus I U2. Solving for U1 and U2 from the above, U1 is equal to 1 upon 2 into T plus T star. Okay. What is this? This is T1. And U2 is 1 upon 2I T minus T star. This is T2. Okay. So after solving this and this, we have U1 is equal to T1 and U2 is equal to T2. That is, T belonging to BH is unique. Hence proved this theorem. Next theorem. Let T be normal and let T1 and T2 be self-adjoint operators such that T is equal to T1 plus I T2, then T1 T2 is equal to T2 T1. Proof. Since T is equal to T1 plus I T2, T star is equal to star of T1 plus I T2. So as above theorem, we have T1 star plus I bar T2 star. Okay. So I bar is minus, that is T1 minus I T2. Since T1 and T2 are self-adjoint operator, so here T1 star is T1 and T2 star is T2. So T is equal to T1 plus I T2 and T star is equal to T1 minus I T2. So we have T1 is equal to 1 upon 2 into T plus T star and T2 is equal to 1 upon 2I T minus T star as above theorem. So we can find T1 T2 and T2 T1. So T1 is this, T2 is this, then T1 T2 is equal to 1 upon 2 into 1 upon 2, that is 1 upon 4I into t plus t star into t minus t star. Multiplying or operating this on this, we have tt plus t star t, this one, and this is minus sign, so minus t star, this and this, that is minus t star t star. Okay, since t is normal, so t star equal to t star t, so this is cancelled out. So we have 1 upon 4I into tt minus t star t star. Similarly, t2 t1, so t2 is this, t1 is this, so 1 upon 2I into 2, that is 1 upon 4I, and t minus t star into t plus t star. So again operating this on this, so we have t plus t star, this minus t star t, this one, and minus t star t star. Since t is normal, then t star is equal to t star t, again cancel. So we have 1 upon 4I into tt minus t star t star. So here t1, t2 and t2, t1 has same value. Here star. This proves the theorem. Next theorem. If T is an operator on a Hilbert space H, then T is normal if and only if its real and imaginary parts commute. Proof. Given T is an operator on Hilbert space H, and let T is equal to T1 plus IT2. Then as per above theorem 1, T1 and T2 are self-adjoint on H. Then T star is equal to star of T1 plus IT2. So solving as theorem 1, we get T1 minus IT2. Therefore, if T is equal to T1 plus IT2, then T star is equal to T1 minus IT2. So we shall find T star and T star T separately. Now T star, that is T1 plus IT2 into T1 minus IT2. So operating this on this, we have T1 square plus I T1 T2 plus I T2 T1 minus I square T2 T2. Okay, that is T1 square plus I common T2 T1 minus T1 T2 plus T2 square. Okay, because this one can be written as T1 T1 minus I T1 T2 plus I T2 T1 minus I square T2 T2. Okay, so this T1 square and I common, that is this is T2 T1 minus T1 T2, and this one is plus T2 square. Okay, that is I square is equal to minus 1, so minus minus plus, that is T2 square. So we have this one. Similarly, T star T. So T star T is T1 minus IT2 into T1 plus IT2. So again solving this as this one, we have T1 square plus I T1 T2 minus T2 T1 plus T2 square. Here given T is normal. Okay. So Tt star is equal to T star T. Therefore, equation 1 and 2 equal. So we have this equal to this one. Therefore, T1 square plus I T2 T1 minus T1 T2 plus T2 square equal to this T1 square plus I into T1 T2 minus T2 T1 plus T2 square. So this is cancelled out. This is also. We have I into this is equal to I into this. So I cancelled out. So we have T2 T1 minus T1 T2 is equal to T1 T2 minus T2 T1. This implies that here T2 T1, here minus T2 T1. So this left side and this one right side, that is we have 2 T2 T1 is equal to 2 T1 T2. Okay. So 2 to cancel out. So we have T2 T1 is equal to T1 T2. That is T1 and T2 commute. Conversely, if T1 and T2 commute, we get from 1 and 2 Tt star equal to T star T. So that T is normal. Because here T1 T2 is equal to T2 T1 because T1 and T2 commute. That is T1 T2 is equal to T2 T1. That is this one cancelled out. So T star T is equal to T1 square plus T2 square. Similarly, here also T1 T2 is equal to T2 T1. That is this part cancelled out. We have Tt star is equal to T1 square plus T2 square. Therefore, Tt star is equal to T star T. That is T is normal. This completes the proof of theorem. Next theorem. If T is an arbitrary operator on Hilbert space H and alpha beta are scalars such that mod alpha equal to mod beta, then alpha T plus beta T star is normal. So we have to prove alpha T plus beta T star is normal. So what is the value of star of alpha T plus beta T star? So star of alpha T plus beta T star equal to star of alpha T plus star of beta T star. Okay, as per the definition of adjoint operator. Okay, so again here alpha beta are scalars. So value of star of alpha T is alpha bar T star and value of star of beta T star is beta bar T double star. Also we know that T double star is T. So we have this one is alpha bar T star plus beta bar T. Now we prove alpha T plus beta T star is normal. That is, first we solve the value of alpha T plus beta T star into star of alpha T plus beta T star. So what is the value of this? So putting the value of star of alpha T plus beta T star here. Okay. So we have alpha T plus beta T star into alpha bar T star plus beta bar T. So operating this on this, This is alpha bar into Tt star plus alpha beta bar T square, and this beta b T star into alpha bar T star, that is beta alpha bar T star square, plus beta T star into beta bar T, that is beta bar T star T. So we know that alpha bar is mod alpha square, and mod beta bar, that is mod beta square. So this can be written as mod alpha square Tt star plus alpha beta bar T square plus beta alpha bar T star square plus mod beta square T star T. This is equation 1. Also, find the value of star of alpha T plus beta T star into alpha T plus beta T star. Okay. Again, putting the value of star of alpha T plus beta T star from here. So we have alpha bar T star plus beta bar T into alpha T plus beta T star. Again, operating this on this. So we have mod alpha square T star T and alpha bar beta T star square, and this beta bar alpha T square and beta bar T star. So alpha bar, that is mod alpha square, and beta bar is mod beta square. So if mod alpha is equal to mod beta, we see that right hand side of equation 1 and 2 are equal. So here coefficient of Tt star is mod alpha square. Okay. Here coefficient of Tt star is mod beta square. And here coefficient of T star T is mod beta square, and here coefficient of T star T is mod alpha square. And these two terms same. Okay. For mod alpha is equal to mod beta, the left hand side of equation 1 and 2 are also equal. So alpha T plus beta T star into star of alpha T plus beta T star equal to star of alpha T plus beta T star into alpha T plus beta T star. Okay. So this is type of Tt star is equal to T star T. Thus alpha T plus beta T star is normal. Next theorem. If T is normal operator on Hilbert space H and lambda is any scalar, then T minus lambda I is also normal, where I is the identity operator. So T such that H to H is normal operator, we have Tt star is equal to T star T. Now we have to prove T minus lambda I is also normal. Okay. So first we find the value of star of T minus lambda I. So star of T minus lambda I equal to T star minus star of lambda I. So lambda is scalar, that is value of this is T star minus lambda bar I star. Since I is the identity operator, so this is T star minus lambda bar I. So T minus lambda I star equal to T star minus lambda bar I. This is equation 2. Now T minus lambda I into T minus lambda I star. Okay. So T minus lambda I into T star minus lambda bar I. Putting the value of T minus lambda I star from equation 2. So operating this on this, we have Tt star minus lambda bar ti minus lambda I t star plus lambda bar I into I, that is I. Okay. So here lambda bar, that is mod lambda square. So value of this is tt star minus lambda bar t minus lambda t star plus mod lambda square. This is equation 3. Again, we find the value of reverse of this, that is star of t minus lambda I into t minus lambda I. Okay. So again, putting the value of t minus lambda I star from equation 2, that is t star minus lambda bar I into t minus lambda I. Okay, operating this on this, we have t star t minus lambda t star I. Okay, minus lambda bar I t plus, this is minus plus, lambda bar lambda I into I, that is I. So again we can write this t star t minus lambda t star minus lambda bar t plus mod lambda square. Okay. So equation 3 and 4 are equal. Okay. This is t star minus lambda bar t minus lambda t star plus lambda square. Here tt star and t star t. Since t is normal, that is tt star and t star t equal. So if this and this equal, so left hand side of equation 3 and left hand side of equation 4 are equal. So we have t minus lambda I into t minus lambda I star equal to star of t minus lambda I into t minus lambda I. This is as tt star is equal to t star t. Hence t minus lambda I is also normal. Hence proved. Next theorem. Okay. If t is normal operator on H, then t star m t n, that is t star power m into t to the power n equal to t n t star m, that is ms power of t star into ns power of t equal to ns power of t into ms power of t star for all positive integers m and n. Proof. Since t is normal operator here given, that is tt star is equal to t star t. If m is any positive integer, we show that t into ms power of t star equal to ms power of t star into t. We prove by induction on m. The result is true when m is equal to 1 by equation 5. Let the result true for m is equal to k and prove it for m is equal to k plus 1. When m is equal to k, we get t into ks power of t star is equal to ks power of t star into t. Equation 6. Now t into k plus 1h power of t star equal to, this can be written as t star into ks power of t star. This and this can be written as t star t because t is normal operator into ks power of t star. Okay. So this into this t star k we can write. So using equation 6, t into t star k is t star k t. So we can write this one t star into t star k into t. That is t star k plus 1 t. Meaning of this is k plus 1s power of t star into t. So this result is true for m is equal to k plus 1. Okay. Hence, it is true for all positive integer m. Now, if n is positive integer, we shall prove that ms power of t star into ns power of t equal to ns power of t into ms power of t star. That is t star m into tn equal to tn into t star m. When n is equal to 1, then t star m into t is equal to t into t star m. Okay. Let us assume that the result is true for n is equal to k and prove it for k plus 1. If the result is true for n is equal to k, we have t star m into tk is equal to tk into t star m. Okay. Now, t star m into t k plus 1. This can be written as t star m into t into t to the power k. That is tk. So, t star m into t can be written as t into t star m using equation 8. Okay. So, this can be written as t into t star m into tk. So, t star m into tk is tk into t star m from equation 9. So, this can be written as this t into tk into t star m. What is this? This is tk plus 1 into t star m. So, which proves the result for n is equal to k plus 1. Hence, it is true for all positive integer n. Thus, we have proved that t star m into tn is equal to tn into t star m. That is, ms power of t star into ns power of t is equal to ns power of t into ms power of t star. Next theorem. Let T be a normal operator on a Hilbert space H and P be a polynomial with complex coefficients, then operator Pt is normal. Proof. Let Px is equal to a0 plus a1x plus and so on an xn be a given polynomial. Then in terms of operator T, that is Pt is equal to a0i plus a1t plus and so on an t to the power n. Since star of tk equal to star of t into t k times. Here we know that the formula t1 t2 star is equal to t2 star t1 star. Okay. So here star of t into t. So in reverse direction we get t star up to k times t star. That is kth power of t star. Therefore, star of pt equal to star of a0i plus a1t plus and so on an t to the power n. Okay. So, as per the definition of adjoint operator, This can be written as A0 bar I plus A1 bar T star plus and so on An bar star of Tn. Okay. So this can be written as A0 I. Here A0 I star is I. Okay. So A0 bar I plus A1 bar T star plus and so on An bar T star N by this property, equation 10. Now ms power of T star into polynomial Pt. So ms power of T star into A0I plus A1T plus and so on An T to the power N. Okay. So multiplying this with this, we have A0 ms power of T star plus A1 ms power of T star into T plus and so on ms power of T star Tn into An. Okay. So by theorem 6, so T star m into Tn can be written as Tn into T star m. Okay. We have proved in theorem 6. So this can be written as A0I ms power of T star plus A1 T into T star m plus and so on plus An T to the power n into ms power of T star by theorem 6. This can be written as A0I plus A1T plus and so on An T to the power n into ms power of T star, that is T star m as common. So this can be written as Pt, that is polynomial of T into mth power of T star. Equation 11. Now here star of Pt into Pt. Okay, so putting the value of star of Pt from this. So we can write this is A0 bar I plus A1 bar T star plus and so on An bar ns power of T star into Pt. Okay. So multiplying this and this. This can be written as A0 bar I Pt plus A1 bar T star Pt plus and so on An bar ns power of T star into Pt. So we have A0 bar I Pt plus A1 bar Pt T star plus and so on An bar Pt into ns power of T star using equation 11. This T star m into Pt is equal to Pt into T star m. So here putting the value of this. So we have this one. So now Pt as common into A0 bar plus A1 T star plus and so on An bar ns power of T star. So this is equal to Pt into star of Pt. Hence here star of Pt into Pt equal to Pt into star of Pt. That is, this is type of Tt star is equal to T star T. So this proves that Pt is normal. This completes the proof of theorem. In this lecture, we have discussed the further theorems of normal operators. These are the references which have been used in this lecture. Function Analysis, Dover Publications, written by George Beckman and Lawrence Naresi. Second, Introductory Function Analysis with Applications, John Whaley and Sons, written by Arvid Krejcik. Third, Function Analysis, New Age International Publishers, written by Biffy Lemieux. And fourth, Function Analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.